And I have to tell you, this is one of my favorite videos, I think, or at least one of my favorite topics. We get to actually use a theorem, Cochrane's theorem, which I think is really cool. Um, and also something I had to review a long, long, long time before presenting this lecture. So um, what I'd like to do first of all is kind of think about some concepts from video number 25, and I think even video 24, where we looked at prediction intervals for certain values of x. So what I want to do is I want to get out and go to R. And I want to remind you of something that, R has certain data sets that are built into it. And one is called mass. And so I just got it. And what I can do now is I can actually go data parentheses and put nothing there. And you can see that I have different data sets here. And I know I've illustrated this to you before. And, I'm going to go down to mass and look at some that are there that I may want to pull up and demonstrate a simple linear regression. I don't know. That looks kind of cool right here. Cars 83. No, cars 93. Wow. Looks like they could have gotten something a little more up to date. But I don't know. Let's use it. So let's go cars 93 to open it up. No warning message, so that's good. What we can now do is do names cars 93 and look at the names of the variables that are included. And we got manufacturer, model, type, drivetrain, rear seat room, luggage room, so on and so forth. Now you can imagine, or at least I can imagine, in a multiple regression setting where we're using multiple predictors, coming up with some pretty cool stuff here. For example, to be able to determine maybe or predict the miles per gallon for the highway. Well, we could use all kinds of different information here to make those predictions. Now, I'm going to show you something. I'm going to get an error, but so if I go mean, for example, price. Now notice I don't get an error because, I'm sorry, notice I do get an error. It's not finding the mean because we haven't attached the data set yet. So guys, I have to go attach, and I have to go cars 93. And again, no errors, so that's good. So now if I go mean price, we can see that the mean price, I'm sure in thousands of dollars, is 19.51. Remember from many moons ago, we could go standard deviation of price. And oh, that's interesting. Well, I forgot I thought it was STDEV. Oh, well, for some reason, oh. No. Well, anyway, I've forgotten the prompt for standard deviation. There we go. So SD. I think it's STDEV, and isn't that in Excel? Maybe, I'm not sure. Doesn't matter. Um, it's something that we can always kind of figure out. So what I may want to do first of all is just go data frame and go cars 93. And what it's going to do, it's going to give me some information here. In fact, it's going to be a lot of information. Let me see if I can get this stabilized here. And notice I've got some categorical data, which eventually we'll learn how to do categorical data in a multiple regression model. We got to create something called dummy variables, which are kind of unique. But also notice that we've got some quantitative data here that we could clearly evaluate in terms of a simple linear regression model. And you know what? I think I'll do that. What I'd like to kind of investigate here is the city miles per gallon and the highway miles per gallon. So let's see exactly how those variables are given. So so we have mpg dot city. Notice mpg is all capitalized, and we have mpg highway. So I don't know. That seems like it might be something kind of interesting to use to predict. We're all concerned about fuel efficiency, or we should be. I get about 28.5 miles per gallon on my car, and I'm actually, pretty happy with that. So, now, guys, first thing we want to do is probably just look at our models here. So, again, we have MPG highway that. Guys, I'm talking. I'm not paying attention to what I'm doing. So we want to do a linear model for MPG. Let's predict highway miles per gallon from miles per gallon in the city. And we can just do model, and you can see that we get our coefficients for our model. So these will be the estimates, obviously, of beta 1 and beta 0. So it looks like in terms of our miles per gallon for the city that for about each additional miles per gallon you get in the city, you're going to be predicting about 0.9 miles per gallon for the highway. Dogs are going crazy again. What about that? Now we can get some more information by going AOV model, and here we get sum of squares and the degrees of freedom, which after the previous lecture should make a little bit more sense. And hopefully this residual standard error down here makes more sense considering the previous videos. Now the next thing I may want to do is I may want to go summary of my model. And when I do that, I get a lot more information just based on the coefficients. Now you might say, well, yeah, but you get some more stuff down here, and you do. You get your these R squareds that we'll talk about actually in the next video. And we get our F statistic and our degrees of freedom. And so, we have a highly statistically significant model here. Now, something I want to point out to you is notice that this probability, this p-value for miles per gallon, turns out to be exactly the p-value for our F statistic. That's going to be true for a while. As long as we stay in a simple linear regression model where we have one predictor, that's going to be true. So again, by the end of this video, we're going to get into the p-value for the F statistic in a lot more detail. Okay, but what I'd ultimately want you to take a look at here is I'd want you to take a look at the ANOVA for the linear model for model. Now what this is going to give us is it's going to give us our sum squares, so it partitions out the sum of squares. Now notice it doesn't give the sum of squares total. It doesn't give the mean square total, which is not a big deal. Because guys, remember the mean square total, the mean square is not additive. So we couldn't add these two values and get anything of value. But it would really be nice for our degrees of freedom and our sum of squares for both the model, which it calls MPG city, and the error, which it calls residuals. These degrees of freedom here, the total degrees of freedom would be 92 because it's additive, and the degrees of freedom for the sum, the sum of squares for the total would be the sum of 2330.28 plus 285.03. Because again, the sum of squares are additive. But again, guys, the mean square is not additive, so if we did include the total here, this would be left blank under the mean square because again, they're not additive. So now, something we talked about a little while ago was how to predict. And if we're just going to focus in on one particular miles per gallon, and just for the heck of it, let's say that we want to predict for 25. Now, we know that we can put that in our model and get an estimate of the mean. But we know because of sampling variation and the underlying probability model that we're going to get a variation from cars with, for example, miles per gallon equal 25. We don't expect every single car with miles per gallon 25 in the city to get the same miles per gallon for the highway. Well, the way we can do that is we can actually, let's see, what I would probably do here is I'll tell you what, let me try this. I'm going to put up here, this is a trial. Okay, I don't know if this is going to work or not. So we called our model, and if I do MPG city equal, just for example, 25, and then I can do an interval here for predict. Let's see if that's what I thought. Okay, that's a bunch of gobbledygook that I don't want. All right, here's what I'm going to have to do. I'm going to have to set this up. So let's go predict 25. And I'm going to have to do data frame. MPG city equals 25. So now I can run a predict for my model, which, you know, what I call my linear model. Predict 25, and then do interval equal predict. Yeah, okay, perfect. All right, so this is what I want. Notice what this gives me is my fit. So if I put 25 in my model, so in other words, I have a city miles per gallon 25. Our model will predict about 31 miles per gallon in the city. But because, again, this varies from car to car, we create the 95% confidence interval, which is the default. So with the 0.95 probability, we can predict that the city miles per gallon, the highway miles per gallon for a city miles per gallon of 25 would be between 27.9 and 34, well, let's say 35. So if we wanted to make another prediction, let's say we want to predict 32. Well, I would go data frame MPG city equals 32 and predict model, predict 32, and let's do interval equal predict. So guys, we would predict the highway miles per gallon for a car that has city miles per gallon of 32 to be around 38, 37.7, with the 95% confidence interval between 34 and 41. All right, gang, that's all I want to do there. I just wanted to show you a couple of things here. I wanted to show you again, and I know we've done it before, but I wanted to just remind you that we have this library mass, and with the data open parentheses, well, parentheses with nothing in there, we can get a list of the data. I chose cars 93 just because I did. Always come in with names, because otherwise you have no earthly idea what the variables are called. And again, make sure you attach these things, because if you start trying to find the mean, It's not going to do any calculations on the variables until you attach it. And furthermore, remember, unlike your professor right now, that standard deviation is SD and not STDEV. So, all right. So gang, let's go for it. Let's go back to the chalkboard and get into inference using the F statistic. All right, gang. First of all, let's just recall that that F is the mean square for the regression over the mean square error. And I have told you, and guys, again, Chris, you brought this up, just what is the difference between the F statistic and the F critical. Well, this is called an F statistic. And our F statistic follows the F distribution with degrees, degrees of freedom for the mean square regression, which is 1, and the mean square error, which is n minus 2. Now, for us to be able to make an inference on R, goodness gracious. For us to be able to make an inference on F, we need to examine the expected value of F. And I think that's pretty obvious because, you know, in a nutshell, we need to know just what is being estimated. Now, we take these things for granted when we, looking at the sample mean mu. And, corresponding X bar, we kind of take it for granted now in terms of beta 0 and beta 1. But, again, what's the expected value of F? Exactly what's being estimated here. So let's, take a look at this. Well, one thing that we know from previous lectures is that the expected value of the mean square error is going to be nothing more than the variance. And I will tell you now that the expected value of the mean square for regression is going to be sigma squared plus theta 1 squared times the sum from I equal 1 to n of x sub I minus x bar quantity squared. Now, you don't have to have a PhD in statistics or mathematics to see that. Let's think this through. Ultimately, what we're doing, we're setting the stage to be able to conduct the inference, and we're going to want to examine. In the simple linear regression case where we have one predictor variable, and I told you in previous videos that we really don't care that much about beta 0. All the emphasis is on the slope, beta 1. So we're ultimately going to want to carry out the comparison of the null and alternative where beta 1 is equal to 0 versus not equal to 0. Now, guys, when the null holds true, when beta 1 is equal to 0, then it's easy to see when we put that in here and square it that this whole term right here becomes 0. So when beta 1 is equal to 0, actually I think I'd rather do that over here. Then we get the expected value for the mean square regression is the same as the mean square for the error, because this will create sigma squared equals sigma squared. Okay? Now, when beta 1 is not equal to 0, what happens? Well, it's really clear that when examining sigma squared versus sigma squared plus this, and again, we have the expected value for the mean square error, and this is the expected value for mean square regression. Fingers getting tired holding this iPad. Okay, so guys, when beta 1 is not 0, it follows, again, whether it's positive or negative, when we square something here, we're going to get a positive number. And obviously the sum of positive numbers, which has to be because we're squaring. So ultimately what we get when B1 is not equal to 0 is we get that the expected value of the mean square regression has to be bigger than the expected value for the mean square error. Now, I don't know if if this is going to really make sense to you, but since we have proven very simply that the mean square or expected value for the mean square regression has to be bigger than the expected value for the mean square error, that we may need to investigate the relationship between the expected value for the mean square regression and the expected value for the mean square error. More specifically, it's to our advantage to investigate the ratio of the expected value mean square regression over the mean square error. Now again, if this number up here is bigger, and as it gets more and more, as it gets larger, then we get a ratio that gets larger. And we know in sampling distributions, as our test statistic gets larger, our p-value goes down, more evidence against the null hypothesis. And so it turns out that this ratio right here is very useful in conducting inferential statistics using the ANOVA table and the F statistic. So guys, let's carry it out. So what we'd want to do is we would want to carry out H sub O beta 1 equals 0 versus H sub A beta 1 not equal to 0, and let's just carry it out. At 0.05. Now we know our F statistic is the mean square regression over the mean square error, and we know this follows the F distribution, degrees of freedom 1, n minus 2. We know that because, I've told you that. But, it's a graduate level class and we need to investigate things much more closely. So, how do we know that our sampling distribution is the F distribution with degrees of freedom one and n minus 2? How do we know that? Well, guys, there's a theorem, and I think it's called the Cochrane theorem, but honestly, I don't remember, and so don't hold me to this, but the theorem goes something like this. It says that if now let me think this one through. If we have n measures, let's just call those y sub I, that come from well, the kids are home, so it's getting ready to get crazy. They come from the same normal distribution with mean mu and variance sigma squared. All right, hold on, guys. Okay, make sure I'm back here. Okay, so I lost my train of thought. Did you have fun? Okay. All right, so oh goodness, okay. So we have n measures, y sub I, that come from the same normal distribution with mean mu and a variance sigma squared. And our total sum of squares can be partitioned into k groups or well, I'll tell you what, let's do this, k sums of sum of squares. And obviously each with their own degrees of freedom. And then each sum of square has that the sum of square divided by sigma squared. Hard for me to concentrate, imagine why. Okay guys, I'm losing my place here. Sum of squares can be partitioned into k groups or sums. The sum of squares, each with their own degrees of freedom, then each sum of squares, which we'll investigate as the sum of square divided by the variance. Okay, I'm back with you now. Are independent. I-squared variables with degrees of freedom being the sum of the degrees of freedom, think for all the sum of squares, if you will, have to be equal to n minus 1. Now, I'm pretty sure, and I don't remember exactly, but look me up on this, and I'm probably spelling it incorrectly, but I think this is called Cochran's theorem, or it could be Cochran. I'm not really sure, but let's go with that. Now, guys, what we got here clearly applies, right? Because, and I'm going to go in here and change to a big old red. Now, red's too much like Ohio State and Louisville. So let's go to good old-fashioned blue pen. All right, so let's go back to this. So if we have n measures that come from the same normal distribution, well, darn it, blue didn't show up. So let's go yellow. All right. So same normal distribution, same mean and variance, and that's all cool. And our total sum of squares can be partitioned into two sums, namely what? Well, sum of squares for the regression and sum of squares for the error. Each with their own degrees of freedom. Well, clearly it is. Sum of squares for regression has degrees of freedom 1, and sum of squares for error has degrees of freedom n minus 2. So each of these sum of squares, each of these, can be viewed as the sum of squares for the regression divided by sigma squared, and the sum of squares for the, regression. Yeah, regression. And the sum of squares for the error divided by sigma squared are independent chi-square variables with a sum of our degrees of freedom be equal to n minus 1. Well, this works out nicely because we know that the degrees of freedom for the sum of squares for total is equal to n minus 1. So the Cochran, well, I don't want to say Cochran because I'm not sure, but the theorem that I have here applies. So the end result is, I'll tell you what, guys, give me 1 minute and I'll be back. Okay, I'm back. It may have been more than a minute, but had to take care of some stuff. All right, so guys, so at the end of the day, what we're saying is, again, the k is equal to 2 because we have sum of squares regression and sum of squares error. So what we can say is that the sum of squares for the regression over sigma squared and the sum of squares for the error over sigma squared are chi-squared variables. Okay? Actually, I kind of like the yellow pen. Yeah, let's go back to white. Okay, now what this allows us to do is examine more closely our F statistic. Which we can now see as being sum of squares regression over sigma squared over its degrees of freedom divided by sum of squares for the error, and you probably see what's going to happen. Our sigma squares are going to cancel out. Which ultimately, this would just give us on top the sum of squares regression over sigma squared. And down here we're going to get the sum of squares for the error over n minus 2 sigma squared. And ultimately, guys, we're going to get into a situation where, let's see, invert and multiply. So, well, I tell you what, this is just pretty simple arithmetic here. We ultimately get into a situation where the F statistic is equal to the mean square regression divided by the mean square error. And, you know, I left dot, dot, dot here. Go ahead and see if you can handle this. I'm sure you can. What ultimately happens is you're probably going to know is these things cancel out and you get exactly what we get, the mean square regression divided by mean square error. So what we can determine there is when B1 is equal to 0, F is a random variable. And with degrees of freedom 1 n minus 2. Now, here's a tricky part, and I gotta admit, I don't even know if I could explain this. I'm not prepared to explain it here. When beta 1 is not equal to 0, we actually get something that's not the F distribution. It actually gets into what's called a non-central F distribution. And I encourage you to look this up if it's something that interests you. I'm not going to cover it because, but nevertheless, we can make calculations. You know, again, let's think of the logic behind hypothesis testing. We're calculating the probability, the p-value, under the assumption that B1 is equal to 0. And so we're making our calculations that way. But this gets really tricky right here when beta 1 is not equal to 0. So look it up. That's all I'm going to say about that. To be honest with you, I'm not prepared to, and it may take me a month to figure that one out because I remember it was very, very, very complicated. So, guys, let's talk about our decision criterion. Remember, first thing we do is calculate the F statistic. And remember, this is going to be equal to the mean square regression divided by the mean square error. The second thing we do is we decide which decision criterion we want to use, whether we want to use the F critical or if we want to use the p-value approach. So I want to illustrate this in R. So let's just say that we get an F statistic equal to 2.5. And we want to look at the F critical and the p-value in the F distribution with degree, whatever, 150. So again, our F statistic equal 2.5. Now I'm going to go to R to make these this calculation. So first thing I'd want to do is let's calculate the p-value. So there I would go PF. I think F is all I have to do. And I would want to go 2.5 degrees of freedom 1, 50. And since that's going to give me the upper tail probability, I've got to go 1 minus that. And we can see that our p-value here is 0.12, which would not be greater than 0.05, so we would fail to reject. Now the F critical value, we would use QF, and since we're working at a probability, a type 1 error rate of alpha level 0.05, and we're conducting a right tail, one tail test, which is customary in the F distribution, we need to have 0.95 to the left of that with degrees of freedom 1, 50. So the line in the sand would be 4.03431 in terms of our F statistic. So if our F statistic was bigger than 4.0341, 4.03431, let me slow down a little bit here, I'm trying to get finished because the girls are home, then we would have statistical significance, meaning our p-value would be less than 0.05. And you can illustrate this. For example, if we take 1 minus PF, and let's go just, let's get sneaky. Let's go 4.03432. All right, and you see what I did. I went just a little bit bigger than the cutoff here. So right here, the cutoff, the line in the sand for statistical significance is this. I added 100 thousandths. So what I'm going to get is I'm going to get something just a slightly bit less than 0.05, which technically would give a statistical significance. So guys, the decision criterion is really, really simple to do, and you'll see, when you do some of these by hand, that the calculation of the sum of squares are actually very easy with just a raw data set. The final thing I want to do here, I think, let me see if I've even got time to do that in this video. Yeah, let's go ahead and pop it out here. It'll take about 5 minutes. Notice that when we've tested versus not equal to 0, we've actually done two things. One time we ran a t-test, and now I'm just confusing things by conducting an ANOVA and running an f-test. Now again, if we go back to R, I think we did that earlier. Notice that our for our t-test, which was conducted right here, obviously because we have a t-value, notice that, and I'm going to write this stuff down, we had a estimate of 0.90, so that was our beta 1, and we had a standard error of 0.033, and we had a t-value equal to 27.28. All right, just to complicate your lives, not really. You can see that when we ran the ANOVA, we had an F statistic of 743.98. Now, under our degrees of freedom here of 1 and 91, let's just see how statistically significant. I know that's kind of like, you know, pregnant, not pregnant, but let's see how statistically significant we are, because for degrees of freedom 191, if we do QF 0.95, 191, you can see that the line in the sand is an F critical of 3.94. We get an F statistic of 743.98, which is a lot bigger. So we, I would say, you know, in this case, we have strong evidence against the null hypothesis. So strong evidence against the null hypothesis in both situations. Remember, this high t-value created the low p-value. I pointed out earlier that this f p-value, the p-value for the f statistic, the p-value for the t statistic were the same. So guys, right now we have strong evidence against the null hypothesis, indicating that the slope of the regression model, which is used to predict city highway miles per gallon from, to predict highway miles per gallon from city miles per gallon, is statistically significant. All right, so let's get into that. It turns out that at alpha level given, that we have an f-test is equivalent to a two-tail t-test. Now, inquiring minds want to know, well, guys, I pointed this subtle fact out to you a few videos back. And it's going to play a pretty critical role in this, okay? So guys, we know that the F statistic can be expressed as the mean square regression over the mean square error, which can be rewritten as the sum of squares for regression over 1 over the sum of squares for error over n minus 2. Now, from this fact, we see the sum of squares regression can be rewritten as this. Better hurry up, I've only got 5% charge left over the mean square error. Now, we saw in an earlier video that the variance of B1 was equal to the mean square error divided by the sum of x sub I minus x bar quantity squared. So guys, no surprise here, the mean square error is going to be the variance B1 times the sum x sub I minus x bar quantity squared. Now, making some simple substitutions here, we can see therefore that when we go back here and go mean square error, and we make this substitution, with this term, these cancel, and we are left with B1 squared divided by the standard error squared of B1. I think that's right. Yeah. Which, if you think about this, what is this? Just t squared. Because you guys remember t is beta 1, I'm sorry, B1 minus beta 1 over the standard error for B1. We are assuming null hypothesis beta 1 is equal to 0. So guys, if we square both sides, you can see that we have precisely t squared. Now, this is kind of cool because if we go back and look at our ANOVA, well, no, we don't need to go back and look at the ANOVA. Let's look at the let's look at what we have right here. We can see that I wrote these down for a reason because I knew this was coming. So if we take our t-value of 27.28 and square that, you know, appreciating the fact that we have some rounding error, we notice that t squared is equal to f. All right, guys, about ready to run out of juice, both literally and figuratively. So this is the end of video. Talk to you later. See ya.